Welcome to our quantum deep dive.
Great to be here.
Today we're getting into something really fascinating. Quantum Simulated Annealing, QSA. Effiziente Problemlösungen. It's an essay by Jörg O. Schneepacht.
Yeah, and it tackles how quantum mechanics can potentially supercharge a classic technique called simulated annealing.
Right. Simulated annealing is used for optimization problems.
Exactly. And optimization problems are everywhere, aren't they? Finding the best route for deliveries, the most efficient factory schedule, the perfect investment mix.
Designing new drugs, new materials, even making AI smarter.
Huge range of applications. But the thing is, these problems can get incredibly complex.
That's what Jörg O. Schneepacht points out, right? That traditional computers, they start to really struggle as these problems scale up.
Totally. They can get bogged down, take forever, or just not find the best answer.
So that's where quantum computing comes in, specifically this quantum simulated annealing, or QSA. It's pitched as a potential way to find these optimal solutions more efficiently.
Kind of a shortcut through that complexity.
So our mission today is really to unpack the core ideas of QSA based on Jörg O. Schneepacht's essay. Where do we start?
Well, the essay smartly begins with the classical version simulated annealing essay.
Okay.
It's actually inspired by annealing in metallurgy, how you heat metal and cool it slowly.
Ah, right. To make it stronger, remove defects, the atoms settle into a low energy state.
Precisely. Essay borrows that idea for problem solving. You start with a random solution, like a random arrangement of atoms.
And then you try to improve it step by step.
Yeah, you make small changes, looking for a state with lower energy, which just means a better solution to your problem.
Okay, so it's like trying to find the lowest point in a bumpy landscape.
Good analogy. And a really key part is this temperature idea.
It's not literal temperature, though.
No, it's a control parameter. It starts high and then decreases gradually, like cooling the metal.
And what does the high temperature do?
When it's high, the algorithm is actually allowed to accept moves that make the solution worse temporarily.
Wait, why would you want to do that? Seems counterintuitive.
It does. But it's crucial. It lets the algorithm jump out of local minima.
Ah, those are the small dips in the landscape, right. Good solutions, but not the absolute best one.
Exactly. If you only ever accepted better solutions, you'd get stuck in the first dip you find. The high temperature gives it the energy, metaphorically speaking, to climb out and explore more widely.
I see. So it can potentially find that much deeper valley, the global minimum.
That's the goal. And the probability of accepting a worse move depends on how much worse it is and the current temperature. There's a formula for it, the Boltzmann factor, essentially. P equals E to the minus delta E over T.
Okay, so as the temperature T drops, it gets much less likely to accept bad moves.
Right. It becomes more focused on finding the absolute best solution nearby as it cools.
Makes sense. Classical essay is pretty useful. You hear about it for things like the traveling salesman problem.
Definitely. But, like we said, Schneepacht notes it can struggle with really complex, rugged landscapes.
Which brings us to the quantum leap.
Exactly. Enter Quantum Simulated Annealing, QSA.
And the big selling point here is quantum tunneling.
That's the star player, yeah. Imagine our landscape again. Instead of having to climb over a big hill to get to a lower valley on the other side,
you could just tunnel straight through it.
That's the quantum magic. QSA can potentially bypass those energy barriers that would totally trap classical SA.
Wow, okay. That sounds like a game changer for getting out of those local minima.
It really could be. The theoretical underpinning comes from adiabatic quantum mechanics.
Right. The essay mentions the time-dependent Schrödinger equation.
Yeah.
Something like IAUG-AOA.
That's the one. The core idea is you start a quantum system in a simple known ground state.
Okay.
Then you slowly, adiabatically change the system's rules. It's Hamiltonian morphing it towards one whose ground state represents the solution to your complex problem.
And if you do it slowly enough,
the system stays in its ground state throughout the process. So at the end, it naturally settles into the lowest energy state of the final Hamiltonian.
Which is the optimal solution you were looking for.
Precisely. It's a fundamentally different way to navigate that solution space.
So QSA is really aiming to overcome those limits of classical algorithms for the really tough optimization tasks.
That's the promise. The essay goes a bit deeper into the theory, reminding us classical SA popped up in the 80s, using those Metropolis Hastings dynamics.
Which gave it that ability to sometimes go uphill to escape traps.
And then it contrasts that with the key quantum concepts QSA leverages.
Like superposition.
Yep. Where a qubit can be, in a sense, both 0 and 1 at the same time. You write it as Hors O's plus 1 ist.
which means it can explore many possibilities simultaneously.
In a way, yes. It provides a much richer state space. Then there's entanglement, where qubits become linked.
Their fates intertwined, even at a distance.
Sort of, yeah. Their measurement outcomes are correlated, and of course tunneling, passing through barriers.
And adiabatic quantum mechanics is the framework that orchestrates this slow evolution towards the solution.
Exactly. And Schneeppert makes a point to differentiate QSA from other quantum algorithms. It's not like Grover's for searching.
Or Shor's for factoring large numbers.
Right. QSA is specifically about finding the minimum value of a function, continuous optimization.
Okay, so it's a specialized tool. Now, how do we actually, bridge the gap, combine classical SA ideas with these quantum features?
QSA essentially replaces the thermal fluctuations of classical SA with quantum fluctuations, driven by that tunneling effect.
So instead of heat energy letting it jump barriers, it's quantum tunneling letting it pass through them.
You got it. And the system's energy is described by that quantum Hamiltonian we mentioned. It usually involves slowly turning off an initial simple Hamiltonian and turning on the problem Hamiltonian.
The equation was like 1 TT, a plus TT.
Something like that, yeah. Where t goes from 0 to a final time at a TT. If our problem gets encoded in.
And the SA contrasts QSA with pure quantum annealing too, right?
Yeah, it does. Classical SA is that stochastic search with temperature. Quantum annealing is often seen as a more hardware-specific, purely quantum process, like what D-wave machines do. QSA is sometimes positioned as more of a hybrid concept, leveraging quantum effects within an annealing framework.
But the key mechanism is still tunneling, allowing these direct jumps to lower energy states, bypassing barriers.
That's the core advantage it seeks to exploit.
Right, so we get the why, what about the how? Implementing QSA seems non-trivial.
Oh, definitely. First, you have to model your optimization problem as that Hamiltonian operator. That's a crucial step, mapping the problem onto the quantum system's physics.
So the lowest energy state is the best answer.
Right. And that temperature analog in QSA isn't physical heat. It relates to the speed of that adiabatic change.
So changing the Hamiltonian too quickly is like cooling the metal too fast in classical annealing.
Exactly. You risk exciting the system out of its ground state, meaning you don't end up at the optimal solution. Slower is safer, but takes longer. It's a trade-off.
And the variables of your problem, like which cities to visit, they become qubits.
Yes, the qubits represent the variables, and their interactions are defined by the terms in that problem, Hamiltonian.
Now, we don't exactly have huge, perfect quantum computers just lying around yet.
No, not quite. So the essay mentions these quantum-inspired algorithms.
Right, running on classical machines, but borrowing quantum ideas.
Yeah, things like VQE, variational quantum eigensolver, or just general quantum-inspired algorithms, QIA. They try to mimic some quantum behavior classically.
But it's not the real deal.
It's not harnessing true quantum phenomena like superposition and tunneling in hardware. Simulation on classical computers is also possible, but it gets incredibly resource-hungry very quickly as you add qubits.
So for genuine QSA, you need actual quantum hardware.
Yes. Physical implementation on machines like those from D-Wave, IBM, Google, that's where the potential for a real speed-up lies, but current hardware has limitations.
Which leads us to the tech requirements. What kind of hardware are we talking about?
Specialized stuff. The essay mentions superconducting qubits, like IBM and Google use. Quantum dots are another possibility. And dedicated annealing systems, like D-Waves.
And what makes good quantum hardware for QSA?
Key things are long coherence times. Qubits need to stay quantum long enough to run the algorithm.
Right, before they decohere and lose their quantumness.
Exactly. Error tolerance, or ideally, error correction, is vital. And scalability, you need lots of high-quality interconnected qubits.
Which is still a major challenge.
A huge one. Noise and errors are the bane of current quantum computers.
And software. You can't just run standard code on these things.
Nope. You need specialized tools and languages. The essay names things like Qiskit from IBM, Cirq from Google, D-Wave's Ocean SDK.
Software libraries to help build and run these quantum algorithms.
Right. And a lot of current focus is on hybrid approaches, software that intelligently splits tasks between classical computers and the available quantum processors.
Okay, so the tech is developing. Let's talk applications. Where could QSA actually make a difference, according to your Schneeppert?
Several exciting areas. Combinatorial optimization is a big one.
Like our traveling salesman.
Absolutely. Logistics, scheduling, network design. QSA's ability to explore many routes and tunnel past suboptimal ones could be huge there. Also graph problems, like finding maximum cuts.
I can see that. Anywhere you have tons of combinations to check. What else?
Machine learning and AI. Optimizing hyperparameters, those tricky settings that tune how well an ML model learns.
That's often a painful trial and error process now.
It is. QSA could potentially speed that up significantly, maybe even influence how we design neural networks themselves.
Quantum-enhanced AI. Interesting. And the physical sciences.
Big potential there too. Material science, chemistry, finding the lowest energy structure for a molecule.
Which determines its properties, its stability.
Exactly. Crucial for discovering new materials, designing catalysts, maybe even finding better materials for batteries or solar cells. Could be big for energy storage research.
That connects to sustainability too. What about finance?
Yes, economics and finance. Portfolio optimization, finding the ideal mix of assets to maximize return for a given risk level.
Another classic, complex optimization problem.
Definitely. Also risk analysis, improving financial models, anywhere you have complex systems with many interacting variables.
So the potential applications are really broad. But let's be realistic. What are the roadblocks? The essay must cover challenges too.
Oh, absolutely. It's not all smooth sailing. Scalability is a major one.
We keep coming back to needing more and better qubits.
Yep. The quantum state space grows exponentially, and the adiabatic evolution for QSA needs to be slow, meaning potentially long run times, even on quantum hardware.
So speed isn't guaranteed just because it's quantum.
Not necessarily, especially with current constraints. Then there's decoherence and errors.
The quantum state just fading away or getting corrupted by noise.
Exactly. QSA needs decent coherence times. Quantum error correction exists in theory, but implementing it effectively requires massive overhead in terms of extra qubits. It's very resource intensive.
So we're still vulnerable to errors from heat, vibrations, all sorts of disturbances?
Right. And then there's the comparison issue. How does QSA actually stack up against the best classical algorithms, or those quantum-inspired ones?
Is the quantum advantage always clear?
Not always, and not for all problems. Classical methods keep improving too. Quantum-inspired has its place. QSA's advantage, that tunneling, is powerful in theory, but its practical performance depends heavily on the specific problem, the hardware quality, and tuning the parameters just right.
So lots of hurdles still. Where does Jurgo Schneppet see things going? What are the future prospects?
The outlook is, well, cautiously optimistic, I'd say. The essay points towards continued development of more powerful quantum hardware.
More qubits, longer coherence, better error handling.
Exactly. Maybe even totally new types of quantum computers or hybrid systems emerge.
And algorithmically.
Further development of those hybrid classical quantum approaches seems key. Using quantum processors like QSA for the really hard parts of a problem, and classical for the rest.
Combining the best of both worlds.
That's the idea. And the potential impact remains huge. Major innovations in science, new materials, drug discovery.
Industry improvements in logistics, finance, energy.
Technology boosts like better AI, better energy storage, maybe even helping with sustainability goals through optimization.
It really does paint a picture of potentially transformative technology.
It does. So, wrapping up our deep dive into Jurgo Schneppet's essay.
It seems quantum simulated annealing offers this really compelling glimpse into how quantum mechanics could reshape problem solving.
Yeah, tackling these incredibly complex optimization tasks that are just out of reach for today's computers.
Now, the path from classical methods like SA to truly effective QSA is clearly complex. There are big challenges in hardware, error correction, scalability.
Definitely not straightforward. But the potential payoff, as the essay highlights, is enormous across so many fields. Optimizing complex systems, driving innovation.
The ideas Jurgo Schneppet presents really push us to think beyond current computing limits, to consider what quantum might unlock.
Absolutely. It leaves you, the listener, with a pretty big thought to chew on. If we could efficiently solve these currently intractable optimization problems, how would that change things? How would it reshape our world?
A fascinating question indeed. Thank you for joining us on this quantum deep dive exploring Jurgo Schneppet's work.
We hope you found it interesting.
And we definitely encourage you to keep exploring this rapidly evolving field of quantum computing. Its potential impact is something we'll likely be talking about for years to come.